Hi, my name is Trygve, I'm Fraser. I'm the CTO and co-founder of Green Cloud, which is an Icelandic cloud solutions company. We offer a public cloud service, but I'm going to spend my talk mostly talking about our software stack, because we also offer a private cloud, hybrid cloud software stack that we call QStack, and I'm going to be talking about the open source components really behind that software. So if we look at the cloud market, then the cloud market, or more specifically the infrastructure as a service market, is one of the fastest, or not if the fastest growing market inside the IT sector. It's estimated to triple in size in just a few years, to be a $230 billion market in the year 2017. And this goes for both hybrid, private, and public cloud spending. And if we look at our software, which we call QStack, then I'm going to be talking about the open source really behind that. And if we look at the open source versus proprietary software, then you find that open source is often, if not almost always, better than commercial or proprietary alternatives. And the reason for that is it has, by some found out to be, have lower defect rates. So it's actually much better in many ways than proprietary offerings, at least in specifically back-end driven development or API-driven development. And proprietary, of course, is often expensive and time-consuming to implement in many ways. So really, if you want to be a player in the cloud market, there's really no way other than not ignoring open source. So this is just such a fast-moving market, so there's so many open source components out there that are doing good things. And today there's really only two ways of developing software. One is the private or proprietary, the traditional one, and the other one is of course collaborative or open source. And if you want to be a player in the cloud market, there's really no way then to look at all the movement that is happening in the open source world. And really a commercial party really can't do, at least a small company, can't really do all the investment in development that is available in the open source projects. And well, we started Green Cloud back in 2010. We started with a public cloud service. But through the years, we have found out that a lot of our customers are actually asking for on-premise installations, or asking actually for the same experience you get from the public cloud, but installed on-premise. So that's how our QStack, which is our software stack, was born. That some of our customers just asked us, they liked the public cloud experience, but for some reasons, technical or legal or whatever, they needed to install the software on site in their data center on their hardware. So that is a big thing that we are actually focusing on. And so our software stack can be deployed in different ways, and can serve actually as all the way from a public cloud to a hybrid cloud to a private cloud. It just depends on the needs of the customer. And I want to spend a little bit time on talk about hybrid clouds, because I think that's quite relevant to this audience, that the future is moving largely to hybrid clouds, or what some people say inter-cloud or cloud federations. But a key component in that really is identity management or identity federations. And the academic sector has built or focused a lot on building strong federations, whether it's national, like the NRANs. So all the Nordnet NRANs have built their own national federations. There are then as well cross-national federations like Kalmar or Edugain, even pan-European ones. And we have actually done some work on implementing support in our cloud solutions for federations. So some of our customers in the Netherlands, we have been implementing support for the Dutch federation called SurfConnect. And, but the same, of course, can apply to any really level in this, whether it's a national federation or if it's a cross-national federation. I think the future definitely is in using these federations as a tool to build more collaboration. So I think these identity federations will bring like an unparalleled new wave of collaborations in the cloud world. And what I think we will see in the future is like a lot of these cloud platforms will be joined together in a federation. And the key in this, of course, is the identity federation. So to have like every university, for instance, could have its own cloud, but it could all be shared in a common pool in a federation. So in our software stack, most of the components, almost all of the components, have an open source backend or root. And on the UI, the user interface side, I show you here a screenshot from our software. It's based on a framework called Meteor. And that is a Node.js framework, so all the code is actually written in JavaScript, so both the server and the client are running in JavaScript. And we started with this about 2 years ago. We replaced an existing framework that was based on an existing UI that was based on Django and Python. And what we found really was that we got a productivity gain by maybe twofold or triple the productivity. Because there's this framework, and the same goes for some other Node.js frameworks, but they just remove a lot of the boilerplate code that you need to do in traditional web development. Because when you can develop both the server and the client side in JavaScript, it just removes a lot of the baggage you have if you develop your UI in other languages, because it's just so fluent and so compatible with the browser, of course. And in this case, we also implemented support or use an open source project called Elasticsearch, which you see there on the screen. That is, Elasticsearch is used like as a usage query engine or search engine. So it's used to graph up, in this case, in the UI. It's actually making a query to Elasticsearch and showing you like the graph of the network traffic on your cloud instances. We also use Logstash, which is integral to our stack to manage logging. So it's a central log repository for all the components in the system. In the compute part, and the API is really an integral part in any cloud solution. We use CloudStack as the backend in our compute engine, and we expose an EC2 or AWS compatible EC2 API. And here I show you just an example of running a command against the API. And in this case, I'm running a tool from another open source project called Eucalyptus, called Yuka Tools. So this is actually a reverse engineering of the Amazon API tools. And so here you can see that the client part is Yuka Tools, but the server part is CloudStack. So you can see that two different open source projects really talking together. The same goes for the object storage. So we actually integrated part of the OpenStack project, which is their object storage engine called Swift. And here in this case, you can see like an open source project called S3CMD that is the client side and then is talking through the S3 API over the internet to the OpenStack Swift service. We have in our stack a lot of other open source projects, so this is just a short list of the main components. We have a large set of other projects that are smaller that we use as well. We use, for instance, MySQL, RabbitMQ, MongoDB, Redis. We use Chef a lot as well to provision software, so we use that as an engine to provision the stack and to automate the deployment and update process. We use Docker a little bit in some of the backend services. We use some Apache components. We use like I mentioned, Logstash and some other components. So, and as well, an integral part in our compute service is KVM, which is the kind of default hypervisor, which is of course in turn part of the Linux kernel. We can support VMware. VMware is kind of the exception here to all the other open source components, but that's an option like as a hypervisor. And we use, for instance, the support in the Cloud Stack for VMware. So Cloud Stack can just talk to VMware as any other hypervisor. So we really couldn't have done this without all of these excellent open source projects. And we have, of course, tried to collaborate in the open source projects we use. So one of the bigger parts is Cloud Stack. So we actually have contributed some of our changes to the Cloud Stack back to the code base, the open source project. So for instance, like I showed you, the EC2 compatibility layer in Cloud Stack. So we actually took part in developing that and donated that part back to the community. So we think that it's really important to give back to the community and donate your code changes back upstream, because that helps everybody and just builds a better community in the cloud market. So what we like to call all these open source projects really enable what we like to call the deployment agnostic cloud, which we mean by that that the customer really can decide his deployment strategy and can really tailor-make the solution to his needs. So we can start small with a few nodes and just gradually add to it. He can select different hypervisors, different storage backends, and so on, and all depending on the client needs. And he can even start with a private cloud and gradually extend that to be a hybrid cloud and so on. So, and this is all made possible really with these open source projects that we use. So, yes, that was it. Thank you.
So we have time for questions. Are there any questions from the audience?
Just a quick question for curiosity. You've explained that you're using Meteor for your web user interface. Meteor is, at least for what I know, considered as a not 1.0 technology. So what's your feeling about it?
I mean, we have been using it for 2 years, even when it was like in version 0.4 or something. I mean, I think it's growing a lot and gaining a lot of momentum. It's been rock solid really for us. It's been really no problems. I mean, the only issues we've had with it is that there have been some API changes and stuff through the development of it. So we have had to change a little bit of the code base, but not really that much, and it's really almost there in 1.0 release. So I think it's really very promising, and I think the Meteor framework is really one example of like the next generation of web frameworks. I mean, you had these traditional MVC frameworks like Rails, Django, and some of the other ones that were kind of, you generated a lot of boilerplate code and stuff like that, but all the nitty-gritty stuff with communicating to the clients, to the browsers, you had to write custom JavaScript code for that. But in Meteor, this is all taken care of by the framework. So for instance, if you are developing something and you want to like refresh a part of the screen in the browser, this is really taken care of by the framework. But in like Django or Rails or something, you have to like wire this specific segment of the screen to a JavaScript callback. But you really don't have to worry about this in Meteor, which is the excellent part, and it's one of the reasons why it has been like accelerated productivity in the UI development for us.
Yeah.
I see like you have a lot of open source components included in your stack. I'm just a bit curious actually how they play with each other, because open source are not really good with each other. They are good individually, but when you integrating them, it's become an issue.
Yeah, so I mean, the key actually to this is one other open source component called Chef, which we use as a provisioning system to configure and wire all these components together. So that is one way that we do it, that we just configure them to talk to each other. So the solution is configuration management. And I think a lot of these components that we use, open source components, are good on their own, but their value actually is compounded by adding them together, by playing together in a very cohesive manner. So I think that's one of the values that we want to bring, is to all these puzzles and bringing them together to a complete whole.
So we have time for more questions. Are there any more questions? No? I have a question. I'm a little bit curious because you offer QCloud for private use. And you're also talking about these federations. Does this mean that you can set up your own private cloud using QCloud and share resources with other identities?
Well, I mean, you can. We haven't started this yet, but we see the trend to this, that this is definitely the future. But today you can, of course, use the QStack to install your own private cloud, but use a public federation for that. So, I mean, even though you install your stack or your cloud on a private premise that is on for instance, on a private network, you can bridge that to the public cloud by federations, and then you could even use that to burst to other clouds. But of course, that needs to be accessible through the internet.
Thank you. Any other questions? Well, let's thank Tryggvi. So our next speaker is Michael de Vos. He's from SurfNet, and he's been working there for 5 years, and he specializes in open exchanges. Let me hum a little bit of elevator music while we wait. 1 second. Michael de Vos.
Okay, thank you, Frey. Good morning. So my name is Michiel de Vos from SurfNet, working at the Department Network Services. Together with my colleague Gerben van Malenstein, who's in front of the row here, well, 2 years ago, we're thinking about how to connect cloud services via Lightpaths, and we came up with an interesting idea we called the Open Cloud Service Hubs, and today I would like to tell you about how we do this with Netherlight. So I wanted to start off with an ancient picture from Kees de Laat of the University of Amsterdam. So on the left you see the number of users, and on the bottom side you can see the requirements that these users have. And Kees divided the users into 3 groups. Group A, which is the part of lightweight users, and if we map this on cloud services, you could, for example, say that these are users that are using email, but also Dropbox, or for example, Skype. So this is actually the part of the internet users. They don't have too much requirements. If we're looking at the right side, there's a category C, which is a small group of users. They have a lot of requirements, looking at, for example, bandwidth or low latency connectivity. So we call them actually the big data user group, and so we're actually already connecting this group of users for a long time via Netherlight to provide big data pipes via what we call light paths, also known as virtual services. And also in the middle there's the group B, which we're actually focusing more and more on. So this is the group which is the business-to-business application part. For example, VMs that we want to embed into local campus infrastructure is also something we want to provide via light paths. At the beginning of this year, we did a survey amongst the SurfNet institutions to ask them, well, would you like to do this? And actually, well, there were 2 outcomes that I want to mention here. The first one is that the institutions are still migrating to the cloud and also still willing to migrate to the cloud. Well, they're also interested in migrating to the cloud using dedicated paths to these service providers. And they have actually, they told us a few points why they would want to do this. So the first one is actually, it has to do everything to do with money. So they want to connect cost effectively to these cloud providers using dedicated paths. And if we look at a simple example like voice over IP, commercial providers are actually selling these services, including a new dedicated service that has to be built to their university. So a leased line, for example. While they are already connected to the SurfNet network and have the opportunity to set up these dedicated paths via our network nowadays externally. So they're looking, they really want this dedicated and high bandwidth via these paths. Also low latency and low jitter is important to them, including the separation from the internet. And they also want to integrate, so that's also important, some of these services into their own layer 2 domain very easily. Well, a top 4 of services that they made. For example, unified communications is one of them. It could be as simple as just voice over IP, but also voice over IP plus services, like the Microsoft link service that is available. Mobile data communications is something that, yes, you couldn't imagine, but they also want to offload this data traffic via dedicated paths. So we did a pilot in the Netherlands using LTE from a commercial provider, where we had a few users of that university using a commercial vendor's LTE equipment and network. And we offloaded their data traffic via a light path directly to their university, so that they would appear in their layer 2 domain and be able to use the local services that were available. Also a video conferencing service is mentioned a lot, but it has everything to do with separation from the internet. So the users want to use this video conferencing, but not over the public internet. And finally, infrastructure as a service, which is quite a big area, goes from backup on-demand services to virtual machines in the cloud. And all these services, we're connecting them, we're connecting a lot of them to Netherlight over the past 2 years. And well, Netherlight is an open light pod exchange that started over 12 years ago. It started as a exchange to support big data transfers for research, of course. And it was also used for innovation, for network innovation to keep ahead and to support the biggest data flows. So, and nowadays we're also connecting cloud services to support our universities using dedicated paths to these services. And this actually gives Netherlight as an open exchange point a new function, which we call a marketplace, to bring these suppliers and consumers together. And these suppliers are actually very happy that we took this role, this independent role, because well, if a commercial vendor would do this, well, that would be a bit difficult for them to sell their services like they're able to do that right now. Also, bringing all these service providers together is stimulating the market around this. So it's easy for our institutes to compare prices and to, for example, compare the available services. So Netherlight, a bit about Netherlight. Netherlight is a single domain, which actually means that a service through Netherlight will never terminate at Netherlight. There are always when a service is built, it always goes from a, for example, service provider towards one of our institutions or somewhere else, and it will pass through Netherlight, but it will never terminate there. Netherlight also does not have its own fiber infrastructure. It's basically only the hardware that we run, and we facilitate actually. We try to facilitate every interconnect using the technologies that are available. So, for example, you could come in with SDH services and leave on Ethernet, or come in double-tagged and leave single-tagged Ethernet frames. Netherlight has an open policy, and this actually means that everyone is allowed to connect. We will not reject any person, provider, institute, commercial vendor. And once you're connected, we will facilitate each interconnect to one of the other parties that is connected to Netherlight. Of course, both of the parties have to agree on that. We try to do this using cutting-edge network technology. And if you want to go internationally, we'll try to use the other open exchanges that we're connected to. So how does this, well, in a graph, how does this look? In the center, there's Netherlight connected, very well connected to the SurfNet network. And we're also connected to several other open lightpod exchanges around the world. For example, Manlan, Xi'an Open, Light. And also, we're able to set up services from one open exchange to another, or, for example, to our big data customers in the Netherlands. Also, we connect with several networks, like, for example, Belnet or the Xi'an network itself. And we're able to set up services, dedicated services, from our institutes, for example, towards these networks. So, and for the past 2 years, we've also been connecting cloud providers. And these cloud providers, well, they're able to bring their services via dedicated paths to our institutes. So, actually, they're also able to set up a dedicated path to each other to, well, to provide, for example, a piece of a service that should also be extended to one of our institutes. Finally, we're also connecting local, what we call regional exchanges in the Netherlands. There are exchanges that own a lot of, for example, fiber, and they're also selling layer 2 services. And behind those exchanges, there are a lot of other vendors. And some of our institutes are already using the services of these vendors. And these regional exchanges are also very happy to connect to Netlight because they only are able to to set up light paths before they were connected to Netlight to a small amount of users. And while extending to Netlight, they're also able easily to set up dedicated paths via an independent platform to other regions in the Netherlands. And also worldwide if they want to, of course. Netlight is Netlight is set up redundant, so vendors are able to connect to 2 locations in the Netherlands. This is actually what is currently connected to Netlight. On the top, you can see several open exchanges, for example, there's a lot of connectivity to CERN, like 320 gigabits at this moment. Also, we're open exchange from Géant, and we're planning to upgrade our connectivity there to 100 gigabits per second. On the right, you can see several networks that we're connected to, like Belnet, the Pioneer network in Poland, the Géant network. And on the bottom, there are several new cloud service providers. So also the bigger ones, like Vodafone, KPN in the Netherlands, Provider, which is a big data facility selling, for example, virtual machines. And on the left, there are some regional networks that we've been connecting. So per October, we'll have some new hardware, which will be a single Shenna 8700 with 8 times 100 gigabit Ethernet interfaces. We will connect twice to the transatlantic ANA 100 gig, well, twice to the other side of the ocean, and to CERN, Géant, NordGnet, and UVA. We also set up a 40 gigabit interface to our OpenFlow testbed, and 20 times 10 gigabit Ethernet interfaces will be available. This device will be able to do Ethernet and also MPLS TP. And it will also bring us the mTOSI interface support, so that you're able to do bandwidth on demand. So to guarantee bandwidth at Netlight, well, first of all, we will not use any classic service classification for our traffic. So what we do is we do ingress policing at all ports and all services. And for the moment, it will be non-hierarchical. So each packet that enters our device will only be policed once. So this actually looks like this. So we're able to polish at each VLAN, and well, we're able to strip the tags and also polish on the customer inner tags. So we're able to do this committed and excessive, which actually means that we, per service, will set a committed information rate that is all traffic that is able to flow through. Some excessive information rate, which is which gives you the ability to burst. So on the left, there's some ingress traffic in this picture. If, for example, you have a committed information rate of 10 gigabits per second, if you if there's not more than 10 gigabits per second amount of traffic, it will immediately go through. If there's more than that, it will go to the EER bucket, And let's say we have, for example, 5 gigabits of EER for this service. If there's less use than 15 gigabits per second in total, it will go through as well if there's availability on the interface. If not, the package will also be dropped. So actually, we're gaining more and more experience. Okay. So we're gaining more and more experience connecting more and more multi-domain services, and so we started to gain experience with a sort of federated operations model. And if you, well, on the left-hand side, there's a small picture denoting a example service between a party A going via network X through Netherlight and exiting at network I to the user B. And so what we see is that, for example, a user A requests a service at user B, so they want to do something together. They ask their networks, network X and Y in parallel, and eventually they will come to Netherlight, and there will be some negotiation, and the service will be set up, hopefully. And this is actually best case. So I've seen this maybe once or twice, and it's pretty difficult to do the setup process. So that is actually why we're also working already for some time on dynamic services via Netherlight. So what a customer would really like within our institutions is that they are able to request a service at a specific provider, and underwater a dedicated path will be set up for this specific service or the set of services that are available. Actually, this is something that we've been doing over the past months together with one of the commercial vendors that is connected. So they were really happy to help us, or to help themselves implementing NSI into their environment. And unfortunately, I don't see Hans Trompert here in this room, but he's the one from SurfNet that has done a lot of efforts to get this implemented. And I wanted to show you a video. So the developer at Kentis is Jos van Bakel, and he's logging in as a user of our institute right now. He's setting up a VLAN service from his institute to the Kentis service right now. So he has to enter his target STP and the available bandwidth. And now the service will be set up. So a layer 2 service is now set up end-to-end from the institute towards the Kentis service provider. Actually, the service has been built now, and he will set up, or he will create a VLAN now with a specific amount of, parameters. Ubuntu machine, creating it now. So once it has been built, he will he will create a new network interface inside the created VLAN. That's something he will do now. And once the machine is set up in this desired VLAN, the user is actually ready to go. And this saves everyone a lot of time, including the Netherlight and the SurfNet NOC, because it flows through multiple domains in this case. So he's logging in to the VM right now. And he will ping the other side, which is an iPerf machine in this case. And as you can see, this actually worked. So this is a first step showing the possibilities of bandwidth on demand for cloud service providers. So we're doing more than that. For example, what happens if another network is in between? most of the most of the vendors at this moment are not so interested in directly implementing BOD because it takes a lot of efforts, and they really need a business case for that. So sometimes it will appear that a network is in between, and they don't support NSI. They don't have an NSA running, Network Services Agent. So if that's not available, we are working now on a solution to do support the service provider on the left to use this BOD solution, while the network in between is not. And this is to provide some uptake, and eventually hoping that these network providers will support BOD. So what we will do here is set up a dedicated SVLAN, for example, and it will generate virtual ports on both sides, such that the users are able to set up services anyways. So the Open Cloud Service Hub would be the perfect situation where a user or university just asks for a virtual machine with a specific amount of parameters for a specific price, and this service, this user or user from a university will, for example, go to the Netherlight broker shop or whatever it is called by whatever it's called, and he will select its desired service at a specific provider, and the provider will we're able to set the service up for this user. So the user requests the service, and underwater the service will be built, and before the user even knows it, he can use this service via a dedicated path. This is also something I've been working on in the Jean project, the JRA1 Task 2, which is called the Open Cloud Exchange project. And we're trying to bridge the gap between the available cloud service providers and the delivery infrastructure to the institute. And we presented a demo at TNC, where we connected, for example, Okeanos and Cloud Sigma to providers of virtual machines via Lightpaths to Netherlight to the University of Amsterdam. And the University of Amsterdam also did a lot of work to successfully create this demo, where we were able to on demand spawn a lot of virtual machines and distribute a lot of frames of 4K movie over these virtual machines, and we're able to even do some real-time transcoding. We're also working on a supercomputing demo for November in the United States, and if you're interested and you will be there, please visit the Xi'an booth. So this was actually the presentation. Thank you.
So, do you have any questions?
Michiel, thank you for a very nice presentation. My name is Friek Dijkstra, Surf Sarah. One of the questions I have actually, in the case of the cloud provider, where does the light path terminate? Well, in this case, of course, it was a simple ping server, basically. And how do you provide the STP to the user?
Yeah. So actually, this can be more and more automated, but the light path is actually, in this case, terminated from the virtual machine on the first side towards the institute's network on the other side. And since they are probably not running an NSA, they will not bring it to the end user. They will bring it to the university's campus.
So something I've been wondering about is, I understand the use case for bringing the cloud service provider to SurfNet through a light path exchange. That whether you do that with peering or light path, that wouldn't matter all that much. But what I don't quite get is SurfNet has a congestion-free, high-speed network that spans the Netherlands.
Yep.
So where exactly is the use case for continuing the light path to the institution? Why wouldn't you just do the traffic over the existing network that you've already paid for?
Yeah, that's a very good question. Actually, doing it end-to-end gives the user full flexibility over what they will do on top of it. So if you provide a layer 2 service end-to-end, they can be able to choose whatever they do on top of this. So at the moment it will be mostly IP, but well, who knows in the future?
And if I may remark,
Of course.
when you look at a diagram of a light path exchange, and
Yep.
you're seeing boxes that say NSA, after Snowden, that might not be the wisest choice of acronym.
Do I need to comment on that? Thank you.
Thank you for an interesting talk as well. My question goes in the same direction, not on the SA, but more the business plan you have. You seem to have put yourself in the spot where you are a service broker. Well, you have users, you have universities, and you have then companies on the other side, and you try to bridge the gap, as you mentioned.
Yep.
You don't seem to build a service yourself. Is this a decision, or is it just convenience, or so for instance storage or VMware, well, this is provided from a company you have entered with. Do the users gain from you making this agreement with the companies?
Yeah.
Because you have all these users, end users at the university. Are this the business plan from SurfNet?
So SurfNet will only actually provide services that are not available on the market. So that is why we probably don't provide the services that we're connecting. On the other hand, we're not the one that makes, so we're not making the price agreements with those vendors. There's another entity within Surf, which is called Surf Market. And they are talking to cloud providers on behalf of our institutes to, well, to arrange prices and to get the best price for these universities.
And if I may, just a quick remark. I think this is a good model. I think you put yourself in a place where there is a need for a middleman to make this arrangement. For instance, Microsoft, you mentioned unified communication. Could every university, we know from Nordic companies, Nordic universities, that many of us use Microsoft Link. So why don't we enter with Microsoft on a big scale agreement instead of each university make their own agreement? That could be interesting for us.
I very much agree. And I think there's also a Géant project, SA7 if I remember correctly, where they are trying to do this.
Just coming back to the question about what the business case is, I think having a service like this allows the commercial providers to offer discounted services to our institutions because they have only to set up the infrastructure once, and it saves, like Michiel was saying, our institutions quite a lot of money because especially in the voice department, the Vodafones were insisting on dedicated lease lines, which are now unnecessary. So I think it's both beneficiary for the speed of the implementation of a service and the costs for institutions.
Thank you.
So, thank you. So our next speaker is Steven Waltz from RNet. One second. So, Steven.
Okay, thank you, Frey. So, a while ago, ARNet started a project to build own cloud deployment. Faced a number of challenges within it. We could go down two paths. We could take a single chassis, own cloud, storage under it, present it to our end users, and profit, basically. But we had some particular benefits with the way Australia and ARNet is deployed. So this is our national network. We have high-speed links between each capital city. To give you an idea of scale, a couple of people have asked me the size of Australia this week. The distance from Melbourne to Brisbane is the same as Paris to Stockholm. The distance from Perth to Melbourne is the same as Lisbon to Minsk. So in terms of geographic redundancy, we've got truckloads of it. We've got at least one POP, generally two POPs in each capital city. We've got links between them, 100 gig backbone. So it's a great opportunity to make a use of it. We've only just in the past 6 months gone to a 100 gig routed network. So very much a white space network to take advantage of. So this is our international capacity. Again, we have that in spades. So what is CloudStor? It's a research-orientated cloud store system, access anywhere, anytime, with redundancy and resiliency. We don't want to have data loss, which is the greatest sin because we've lost a POP. But we need to remain secure and sovereign. A lot of the time when researchers will get funding with an Australian government research grant, the data has to stay within Australia. It can actually be of commercial benefit to Australia. So if you put it on Dropbox or similar, it can end up in the US, or it can end up in another entity who may, if there's a commercial usefulness to that data, may do nefarious things with it. OwnCloud is the primary building block. We use simple SAML PHP in front of it as the federation service provider and directory. We use a layer 7 TCP accelerator, HA proxy for speed. We use Anycast addressing on the nodes within the network just to allow us to have better proximity network-wise to the end users. Every researcher, every time from the second they log in, gets 100 gig of storage. And that's determined by a flag their institution returns. So we don't need to do anything, they don't need to do anything. It's very much a case of go to the site, log in, straight away they have 100 gig. The hardware for this we used was the Supermicro chassis, 36 drives in a 2 drive sled. RAID 0 on the drives means that we get the extra space and it's just a matter of pulling a sled to upgrade. We're using the Western Digital Red NAS drives in those just because we're after that better lifetime and sustainability of the drives. So when we looked at it, we figured that we could take advantage of this POP in every city and we could deploy this wonderful, great network. So we'd have disk stores with layer 7 accelerators, the HA proxy, in every capital city and in places like Alice Springs, which is the middle of nowhere, where we still actually have quite a large number of researchers. We could just put in a layer 7 accelerator chassis. We were hoping to push out to Seattle in the US and Auckland in New Zealand and up to Singapore from the Perth run. What we ended up with is very much different. And it came down to bang for buck, we could do a similar network availability with this model. I will get to a couple of things different about it later in the talk, but the important things are when the Snowden revelations came out, suddenly the fact that all of your Dropbox data is in the US suddenly became a really, really big issue for people overnight. They were quite happy to shovel loads and loads of data out, and then suddenly they didn't want that and wanted to shovel it back into Australia. They want them everywhere, but they want them secure and safe. So whilst we might be providing SSL front end in Seattle, we were still going to be traversing the SX transport fibers to replicate that data. And one of the revelations that came out in Snowden is that when that network was built, there was an agreement reached between the company at the time and the American government. So it's 2014, well at the time it was 2013, and storage is a solved problem. Well, that's what we thought. We started off with Hadoop MapR, provided a solid, like rock solid NFS server. We never had a problem with the NFS component. Storage is still, the file system is still de facto. You have to have a file system under every cloud store, under every web server and the like. They can't deal with objects. They need files. You have to have a POSIX compliant system in there. The 3 nodes need to remain in quorum at all times. So we have Melbourne to Perth is 36 milliseconds. Melbourne to Brisbane is about 28, but Brisbane to Perth is 64 milliseconds, but the MapR quorum timeout is 63 milliseconds. So we'd have periods where we got some very, very good latency between Brisbane and Perth at the start of the project, and we were happy. And then the university holidays ended and students came back, and suddenly our latency changed by 2 milliseconds, which is more than enough to make the whole thing blow up. The incoming it was quite a surprise to us that it was going to be that difference of 2 milliseconds, but it took us a little while to work out why the cluster was just reaching just randomly, deadlock, hang, require human intervention. It's always the 2 a.m. rule. It's the system will always break 2 a.m. after you've spent all night at the pub or at a party and you're really in no position to try to work out what's happening. MapR is still a good system. It's a great product. We may very well use it elsewhere. It's just in this use case, it just really didn't work for us. Next on the table was XtremeFS. So it ticked all the boxes in investigation and in the lab. File system was file system driver and tools were a little rough. We cut some code and cut some more code and then cut some more code. Cut a bit more code, and then everything blew up and Perth dropped out of quorum and wouldn't come back in and wouldn't sync. And it took us probably about a month and a half after we moved away from XtremeFS to find out that the Backbone guys had made a minor change to the path, had added in a single hop just outside of Melbourne, and had added 1.5 milliseconds of latency to the Backbone, which was enough to tip it over the edge. Again, it's a really good product. We'll be using it elsewhere, but not for this sort of a thing. You also have to account for array rebuild issues. One disk failing takes 5.5 hours to rebuild within an array. You lose a chassis and you're moving up to 216,000 seconds or 53 hours to rebuild. So if we lost a data center for long enough that the system decided a full resync or rebuild was better, we were going to be pushing data flatlining into that node for a little over 2 days. If we pop those 3 terabyte drives out and replace them with 8 terabytes, then we're getting up into over 6 days, nearly 7 days to resync a chassis, at which point it's almost easier to go back to shipping a pallet full of disks around the country. But then, of course, you've got the problem. Once you've finished rebuilding and syncing all the array, there's then nearly 7 days worth of delta on the other nodes that still needs to sync and catch up. So it's not a matter of starting a stopwatch and saying 7 days, we good, you know, we're back in it. You can have an undefined period of time as it tries to catch up. So our current solution is an active-passive system. We have one node that we denote as active. We use the University of Chicago's UDR, which is rsync over UDP, to push data around. It's about a 5-minute delta. We did have a situation with a researcher who decided to clean up his drive, made a mistake, jumped onto his desktop, which hadn't yet synced, to try to do it all over again. And then after he spent about 7 minutes doing it, decided to mail us to say something's gone wrong and I've lost all my files. We got the ticket and logged into the last box just as the sync finished and completely removed his home directory. So you have about a 10-minute window where things happen, but it always happens. You always get notified about it at the 11th minute. Again, RNet is a white space network. We've got bandwidth to burn. We're happy to use it. The initial sync that we did, we just started it off at midnight one night and flatlined between the nodes to get the data over. In terms of a front end in there, we're running HA proxy. It traverses the distance on behalf of the user. So we can control the server it's on. We can tune the TCP stack on the server, but we can't control the end user. We don't know what they're running. We've seen header information from people running XP and older versions of Windows where they're not tuned. So we need to allow for that. So we need to push the front end as close to them as we can and then control the window size between the proxy and the storage. So we could pull it back and just do storage all over again, but we're not giving up. There's ways around it. Users don't notice. We did have one user that was complaining of absolutely terrible transfer and sync when they were uploading files. And we ended up pushing it right out to our edge server at their institution and just dropped a proxy on that so that we had just their network and they were syncing to that. And we could actually determine that it was one of their routers was causing grief. So that ability to push a proxy right up close to the end user is what makes it a lot simpler. As I said, we've got the CPE servers, we can push it out, but of course, we're also in the middle of rolling out a new network, RNet4, which does away with those edge servers. So, our solution is that our new mirror, which we're also rolling out as a CDN, has a series of front ends. It's using Apache Traffic Server, but there's capacity on those nodes to be able to fire up HA proxy, anycast another address, and push that close to the customer. Strangely enough, the RNet CDN puts a cache node, cache front end in every capital city. So we're basically going back to our original design of having a cache node in every capital city with storage in 3 major centers. There's obviously, it's no point having a highly available storage backend if you don't have any database in there to track that. So we went with MariaDB. We used Galera for the quorum. National quorum, read bandwidths, puts it as good as a local-only database. We can pull stuff out of it really fast. The read-in speed for OwnCloud, the write-in speed isn't limited by quorum decision. So if you only have one node and you're bringing everything back up, it will read in at the same speed whether you've got 1 or 3. The cluster stops require a human decision as to which node to bootstrap from. Very, very rare event after we moved away from MapR, because obviously when MapR locked up the entire chassis, we'd lose quorum, so we'd have to go back and start again from scratch. 5 terabytes of insert and update and over 365 days of quorum as of September 10th. And then September 12th, we hit a kernel bug that dropped out networking on 2 nodes and lost quorum. So yeah, we've had over a year of quorum allowing for that, and that's with maintenance in there, work, both work on the chassis, work on backbone, and the connections that they, the routers they're connected to. So the lessons we learned is that distributed multi-site storage is really hard. There's a point where you just don't fit anyone's idea of what the product should do. You're too big to use the small stuff. So we would have loved to use Ceph, but we're going a very wide footprint, and the latency would have killed Ceph. But we're too small to use the big stuff. We can't do the Google way and just hire a couple of software engineers and have them hammer out a clustered file system for us that's distance neutral. New and shiny is often shiny for a reason. It's not the best to use. We spent a period of about a month where we were just trying every new disk and storage system that came out to see if we could do it better. And it'd be 3 days of work, and then we'd push it to one side and start on again. And after a while, it was just a waste of time to try to do anything more. But sometimes there is a valid technical solution to a social problem, the social problem of people not upgrading from Windows XP. Well, the technical solution is push your storage nodes out as far as you can to those users. The simulations can only take you so far. We were using the Linux TC utility in the lab to actually model a lot of the network behavior we were expecting to see. But that only worked so far. We hit a problem with the Cisco 7600 TCP ramping where it just didn't follow any model that we could find. And we went mad trying to work out what it was. Okay, I have a duplicate point in there. Just because you have all the disk, it doesn't mean you have to use it all at once. So what we ended up doing was we took a third of our available disk and we built that up to use with MapR. When that ceased to be a valid solution, we took another third and built it with ExtremeFS and synced the data from MapR to ExtremeFS, which meant that when we flipped from MapR to ExtremeFS, there was less than a minute of downtime because it was simply a matter of stopping the service, remounting the drives, bringing the service back up, letting it index, and we were back online. It makes it very easy to test new technologies or to see if a developer comes back and says, no, you've done this block size wrong when you did your initial tuning, you need to change your block size to this. We actually have the disk to do that. We don't have to pull the node out, rebuild it, then resync the data, and then find out if we have any benefits. One of the problems that's catching us at the moment is the continual thinking of objects being the same as files. So there's file store and there's object store. And in a perfect world, we'd love to go object store because it makes it really simple. But the requirement for a lot of things like OwnCloud and Apache is that it's a file system. It's a file. It can point to a POSIX file link and say, this is what I'm trying to find. So there's another project running, which is a Australian federal government project called Nectar, the National E-Research Compute Project. OpenStack-based compute nodes in various capital cities. They use Swift as a back-end storage. So we figured, hey, what if we backed CloudStor Plus into Nectar? But CloudStor doesn't do object storage. So we're back to this problem of we've got files, we need to deal with objects. So what we've done is worked with Nectar to drop some experimental code in to export a user folder into their into Swift storage to be exposed to Nectar. Our plan for this eventually is when we move to OwnCloud 7, which has the Swift support, is that we will have a local SSD, a local PCIe SSD cache, so the data will get pushed into that. It will then drop into Swift's ring storage, and Swift will take care of it for us. At the moment, we're just testing this to see if it's a valid idea. It's just something that we kicked around one afternoon. We did roll out and duplicate our entire infrastructure again. So we now have a user acceptance or a testing system, which is the same design. We have the nodes and the front ends in Brisbane, Melbourne and Perth, but these are purely for testing now. So we can push several terabytes out to something like Nectar, and we can push several terabytes to another compute project, and we have a university that's wanting to look at a solution that some of their PhD students are working on. So it's not the end of it. We're not giving up. We've hit some bumps. We think we're over them. We're patching the road as we go, but that's really where we're at. So at this point, it's any questions?
Hi, thank you for the presentation. It was
thank
really interesting, and especially the distances down there make this multi-site cluster synchronization thing a bit of a problem. So my question is, I didn't really understand how does the end users access their storage?
Sorry, so there's several ways they can access it. They can go to a website and they can log in, so cloudstore.arnet.edu.au/plus. They get the nice web interface, they can drag and drop files or upload it. There is there's a client which talks, and it just left my brain what the name is. There's a client that talks to the front end. We have actually worked out a way to inject files into users' directories. So apart from the fun you can have with that with workmates, Arnet runs a video conferencing recording service. So when a lecturer uses our video conferencing service to deliver a lecture, they can record it, and that lives on a separate system. We've now worked out how to take files recorded from that system and inject them into their home directory. But at the moment, it's via a client, so either a desktop or a mobile client or a web interface. So, does that answer the question, or? Yep, okay.
Thank you. Thanks. So you seem to have done a really large amount of investment in building your own storage infrastructure around this. And there's a cynical part of me that says, well, could you have phoned up Box, Dropbox, or someone, or the other guys like that, said, look, what are your plans to build an instance in Australia and to sort of do zones or something like that to keep Australian data in sort of in Australia? Did you explore those options?
We have an agreement with Box already to provide universities with a group plan. This was just something that we wanted to do as a homegrown guaranteed. The big thing for us was the data sovereignty. If it's our system in our network, on our network in our POPs, we have control of where the data goes. The solutions like Box and the like are very much, all your data will be in Australia, but just to be sure we'll ship it off over that way or off this way just to make sure that it's all safe. So those options were initially explored, but they weren't compared with the benefit of a solution. They were compared as we can build a solution that provides 100% data sovereignty. Can they provide a similar service? And that was its benchmark of being assessed.
Okay, thanks.
Okay. Oh. That
To follow up on the previous question, so have you got an idea on what, if you don't count the research type of time that you have to use, so from a purely operational point of view, have you got an idea on what the cost roughly is to provide this to your users?
We don't, but it came about from the original engineer that worked on it, having an itch and scratching it and wanting to do it, and he had some spare cycles and he had some spare hardware in a VM environment, and he spun it up and we did a proof of concept. But we're actually using it very heavily internally. Everyone, as soon as they find out that it's there, throws the sync client on their desktop, puts sync client on their phone, starts shoveling files and presentations and data they need into it, because it's the access anywhere, anytime. To access your home directory, you need to be logged in, or you need to be VPN'd in, and you need to have the mappings active. Whereas if it's this service and you're at the Nordgenet conference and you decide, oh, hang on, we discussed this, let me pull that paper up, it's just simply a matter of logging in and it's there. So the cost-wise, I couldn't really put a figure on it, but it was myself and another engineer doing this as part of our other day job. So we weren't 100% dedicated to the project, but it was myself and another engineer working on this over the course of about 6 months to get it fully ready and operational. Oh, sorry, there was some coder time in there. We hired a coder to just take some rough edges off some of the plugins we used and do things a little bit better with the way it handles federations.
Thank you. I would just like to ask you, the network infrastructure for supporting those different storage boxes, how is that? Is it a routed network? Is it a private network? Or is it a VLAN where those boxes exist?
The boxes exist on a traffic VLAN off the router, just so that the router they're connected to is our peering router in each state. So we actually use a VLAN to get our internal traffic to them, but they anycast an address. So there's the address for the server itself to sync data between, and then there's the anycast address, which is the one exposed to the public. And that anycast address is dealt with separately within our network over dealt with separately over that public one. It's not, there's obviously, locally on the box there's firewalls, there's access control lists on the routers, so it's not possible for someone to access the underlying system from outside our privileged network. There's only that anycast address that they can hit. Last call before coffee. Oh.
Let's thank Stephen Walls. I have a few announcements. If you need your boarding pass printed out or a taxi, then the people in the reception can help you. Also, if you want to keep your luggage here, we have room for it here in the wardrobe. That's not behind the counter. Thank you.